Alright, so the next step is to apply these concepts of the mole and mass relationships to chemical equations. So we said that the coefficients then in a balanced chemical equation tell how many molecules and thus how many moles at the large scale of a reactant are needed and how many molecules and then moles at the large scale are going to be produced. So if we have our example below, we could see that 3 moles of hydrogen gas plus 1 mole of nitrogen gas is required to make 2 moles of ammonia. So this becomes useful if we want to calculate how much of each of these substances we would need to add to our reaction vessel to get them to combine. So we can use our coefficients in our chemical equations as mole ratios. So remember, if there's no coefficient listed, that indicates that there is a 1 before this nitrogen molecule. So in the synthesis of ammonia, the mole ratio of hydrogen gas to nitrogen gas is 3 to 1, right? It's going to take 3 moles of hydrogen for every mole of nitrogen to make 2 moles of ammonia. So we can do molar ratios then for any of the substances on the reactant side or between the reactant end product side. So we could say that the mole ratio of hydrogen gas to ammonia is 3 to 2. So for every 3 moles of hydrogen gas, it's possible for us to make 2 moles of ammonia. And then the mole ratio of nitrogen gas to ammonia is 1 to 2. For every 1 mole of nitrogen gas, if our hydrogen's unlimited, we could make a total of 2 moles of ammonia. So this leads us to make the following conversion factors. We can have 3 moles of hydrogen gas is equivalent to 1 mole of nitrogen gas. 3 moles of hydrogen gas is equivalent to 2 moles of ammonia. And 1 mole of nitrogen gas is also equivalent to 2 moles of ammonia. And you could write these in the opposite formats too. It doesn't matter which one is on the top or the bottom. That's going to be determined by what you're trying to calculate. So if you were trying to calculate the number of moles that you would need of hydrogen gas, then that would be on the top. If you were trying to calculate the number of moles of nitrogen gas that you needed, then that factor would be on top, and moles of hydrogen gas would be on the bottom. So just like all of our other conversion factors, we can place them either on the top or on the bottom because each of our conversion factors is essentially equal to 1. So mole-to-mole conversions then are carried out using our mole ratios as the conversion factors, and we'll see some examples of this coming up. So if we know the number of moles of A that we have, we can calculate the number of moles of B that we would expect to get out of our reaction. And we can do this by using our mole ratio as the conversion factor. So in the last section, we were doing mole to mass and mass to mole conversions, and we saw that these are carried out using the molar mass of a compound as our conversion factors. So how many grams are there per mole of a substance? And then we can use that to calculate the gram weight. Or we can use that to calculate the number of moles that we have present. So mass to mass conversions are frequently needed, but they cannot be carried out directly because the mass of one substance is not equivalent to the mass of another substance. And so you have to do that indirectly by moving through the mole conversion. So overall, there's going to be 4 steps to help us determine the mass relationships within our chemical equations, since our chemical equations are written in concentrations of the moles. So step 1, you need to write a balanced chemical equation. So we've been practicing that in chapter 5, and we'll get more practice with that in chapter 6 as well. Then you need to choose the molar masses and the mole ratios to convert known information into the needed information. So you do this, and then you set up the factor label expression, and you calculate your answer. So if you have given the grams of substance A, you should be able to convert that with your molar mass, right? So you'd be able to look that up on the periodic table. So A would be a substance. If it was carbon dioxide, for example, you would be able to calculate the molar mass of carbon dioxide, and you could convert grams into moles. You could then use your relationship that is inside the equation. So if you had carbon dioxide combining with another molecule, you could say how many moles of B would you need to combine with it? And you would use the molar ratio in the equation. So this would be equivalent to your coefficients in the chemical equation. Once you've calculated how many moles of B that you would need or that you would have after the reaction occurred, you could then convert that back using the molar mass of B to calculate the grams of B. And both of these then, grams of A and grams of B, are things that you can do inside the lab. So we could actually physically weigh these substances. We can actually do those in the lab. So the first thing we need to do is we need to write a balanced equation. So here we've got an equation for making water from hydrogen gas and oxygen gas. We can see that this equation is balanced. So we've got 2 moles of hydrogen gas combining with 1 mole of oxygen gas to make 2 moles of water. And you can see all the phases in here of each of these substances in the gaseous phase. So we can write down conversion factors. So these are our mole to mole conversion factors. So we know if we are going to make 2 moles of water, we're going to need 2 moles of hydrogen gas to do that. So this one will reduce to a 1-to-1 mole ratio. So 2 and 2 are going to cancel. So for every 1 mole of water that we make, we're going to need 1 mole of hydrogen gas. So if we have grams of hydrogen gas that we can measure in the lab, we want to convert that to the moles of hydrogen that we have, and then we can calculate by our mole ratio how many moles of water we should make. We can convert this back into grams of water, and this is something that we can physically measure within the laboratory and see how close that we got to what we would predict. So if we want to know how many moles of water are produced from the combustion of 4.11 moles of hydrogen gas, how are we going to do that? We start out with moles of hydrogen gas. We need to convert that into moles of water. So that's going to involve the center part here, where we evaluate our mole relationship from the equation. And so we do that by evaluating what we have. We have 4.11 moles of hydrogen gas, and then we need to use our molar ratio from the equation to calculate the moles of water that we're going to get. Our molar conversion factor was 1 mole of water is produced from every mole of hydrogen gas used. So this one's an easy one. It's a 1-to-1 conversion, and so essentially multiplying anything by 1 is still going to be the same number. So if we have 4.11 moles of hydrogen gas, we should be able to make 4.11 moles of water. So in this equation, we're asked how many grams of water are produced from the combustion of 0.500 moles of hydrogen gas. So we can take that one step further. So this is evaluating our mole to mole conversion, so our mole relationship. And then we need to use the molar mass of our water molecule to calculate the grams of water present. So if we start this equation, we start out with what we have. We have 0.5 moles of hydrogen gas. Our goal is to get our answer in grams of water. So we still have our molar conversion factors, and we still know 1 mole of water is going to be made from 1 mole of hydrogen gas. So we can put that in there first and calculate moles of water that should be made from half a mole of hydrogen gas. The moles of hydrogen gas cancel out, and we're left with moles of water, in this case 0.5 moles of water. And we also know our conversion factor 2 is going to be related to the molar mass, so that we can convert moles of water into grams of water. In this case, since our goal is to calculate grams, we're going to want grams on top. And so we'll put this conversion factor in. Our moles of water will cancel out, and we'll be left with our answer in grams. So we can see for half a mole of hydrogen gas entering, we should produce 9 grams of water out on the other side. So we could evaluate that in the laboratory setting. So now we want to know how many grams of hydrogen are required to produce 148 grams of water. So this requires a gram to gram conversion, and we said we can't do that directly. We have to go through the mole conversions first. So we have to evaluate what we have still. That's going to require that we use this entire set here. We go from grams to moles, and back into grams. So in this case, we have 148 grams of water. So that's evaluating what we have. We need to find how many grams of hydrogen gas do we need to add to our equation to get this many grams of water. So first thing we need to do is we need to convert back into moles of water, because that's how we evaluate our equation. So we know that we need, for every mole of water that we make, we need a mole of hydrogen gas. So to compare this to hydrogen, we need to convert our grams of water into moles of water. So we can do that using our molar mass and our molar conversion. This time grams is going to be on the bottom because we want to get rid of them. Moles is going to be on top because that's what we want to find. So we can see if we multiply this through, our grams will cancel out and our answer will be left in moles. So 148 grams of water is equivalent to 8.2 moles of water. We then use our mole conversion, which is going to be 1 mole of hydrogen gas for every 1 mole of water. We'll put that guy in there. The moles of water go on the bottom, moles of hydrogen gas on top, because that's what we want to calculate. Our moles of water are going to cancel out. We'll be left with moles of hydrogen gas, which is 8.2 moles. And then we need to do one more conversion, right? We need to convert now from moles of hydrogen gas into grams of hydrogen gas. And for that, we need to use the molar mass of hydrogen gas. So we'll write that one out on this next slide since we're running out of room. So we've got our 8.2 moles of hydrogen gas, and we know that there are 2 grams of hydrogen per mole of hydrogen gas. So we just add the sum of the 2 hydrogens here to get the molar mass. And so moles is going to go on the bottom since we want to cancel that out and we want to get our answer into grams. So if we multiply 8.2 by 2 grams of hydrogen gas, we would predict that if we had 148 grams of water produced, that we would need to put in 16.4 grams of hydrogen gas. So this is an example of how we can use our gram to mole conversions and the mole to mole conversions that we learned from our chemical equations to calculate either how much of a substance we need to get a given volume of a product, and this involves both the gram to mole conversions and our mole to mole conversions. So we'll get some more practice with this in class.